Hello everyone. After studying about the free particle, its eigenvalue and eigenfunction, let us move on to the next application, which is about the particle in an infinite square well, where we will be finding out its eigenvalues as well as eigenfunctions. First, let us understand what actually is an infinite square well. So here we can understand that the particle is not 100% free to move, but it is confined within the square well. So in infinite square well, we are having potential V of x along y-axis and position along x-axis. And I am taking the extension of square well from minus a to plus a. And at the barrier or at the boundaries of the square well, we have potential equal to infinity. And that's why it is called as infinite square well or also called as infinite potential well. So the particle which will be present within the square well, it is free to move. It won't be at rest. And that's why the potential V of x will be equal to 0 and it will be having its own kinetic energy. But at the boundaries or outside the boundaries, the particle won't be present, because the particle, if it has to come outside the barrier, means it has to acquire a potential of infinite order, because the boundary is having the potential equal to infinity. That's why the particle cannot have that much high potential and the boundaries are acting as impenetrable barriers. Means the particle of mass m will be trapped within the square well itself. It cannot be present at the boundaries or outside the square well. So let us define the potential, which is V of x is equals to 0 within the square well extending from minus a to plus a, and V of x will be infinity for other cases, that is at the boundaries and outside the square well. Let us call it as equation number 1. Then based on this knowledge, we can just say that at the boundaries we cannot find the particle. So the probability of finding the particle at x is equals to minus a is 0, and also it is 0 for x is equals to plus a because of infinite potential. And based on this, we can say that xi of minus a is equals to xi of a is equals to 0. Let us call it as equation number 2. So from this we can understand that the particle is not at all present at the boundaries or outside it. So for the eigenfunction or eigenvalues of the particle, we need to concentrate our study within the square well itself. So for that, let us consider the equation of motion of quantum mechanics, which is the Schrödinger equation. Here we are considering the time independent case, that is time independent Schrödinger equation, which means the wave function is only depending on position and not time. It is given as h xi of x is equals to E into xi of x. As potential of the particle within the square well is equal to 0, Hamiltonian operator will be only due to the kinetic energy, that is minus h cross square by 2m d square xi of x by dx square is equals to E into xi of x. Here I am considering the definite differential because xi is only depending on position and not time. If it was having two different variables, then we can take the partial differential. As we have done in our previous application of free particle, we have to just rearrange the term, and we know that 2me is equals to p square because p is equals to root of 2me, and p by h cross is nothing but k, which is a wave vector. That's why we are having equation number 3, which is again the same type of equation as in our first application, which is with respect to free particle, and here it is seen that it is again a second order differential equation. So the corresponding solution will be equal to xi of x is equals to a sin kx plus b cos kx. So let it be equation number 4. Then we need to see what happens at the boundaries again. So we have v of x is equals to 0 for the particle within the square well, and when x is equals to plus or minus a, we have xi of a plus or minus a is equals to 0. That is what happens at the boundaries. So in order to understand or in order to get the constants a, b as well as to find out the value of k, we need to consider or apply the boundary conditions so that we find out these constants. So when you apply boundary condition means we just need to see what happens at x equal to minus a and x equal to plus a for xi of x. So let us consider at x equal to a. So when we put x equal to a in our equation number 4, we get xi of a is equals to a sin ka plus b cos ka. And as we have already seen in our equation number 2, xi of a will be equal to 0. So let it be equation number 5. In the same way, we need to find out what happens to xi at x equal to minus a. Again, xi of minus a will be equal to minus a sin ka, because sin of minus theta is minus sin theta, but cos of theta is equals to cos of minus theta. So first part we are having a negative sign and it is again equal to 0, which is from equation number 2. Let it be equation number 6, and in order to find out a and b, let us solve it like a simultaneous equations. So equation 5 plus equation number 6, we can see that first part, that is a sin ka minus a sin ka, will get cancelled out and the second term will add up, giving us 2b cos ka is equals to 0. So when you solve it, we can just say that b is equals to 0. There is a chance for cos ka equal to 0 also, but at the boundaries, let us see what happens. So from this equation, either b will be equal to 0 or cos ka will be equal to 0. Then when you add equation 5 with equation 6, you have the value of b. Now when you subtract equation 5 from equation 6, second term is going to cancel out and first term we are having minus 2a sin ka is equals to 0 or plus 2a sin ka is equals to 0. From this we can again say that a is equals to 0. But one thing we need to remember is, at a time both a as well as b cannot be equal to 0. Because if that happens, then xi of x will be equal to 0, which means there is no particle within the square well, and that cannot happen. So what we are going to do here is, from the addition of simultaneous equation, we have two things. One, either b will be equal to 0 or cos ka will be equal to 0, and from the second, that is subtraction of these two equations, we can say that a will be equal to 0 or sin ka will be equal to 0. So let us solve in different cases. So case number 1, here we are considering one term that is equal to 0 and other is not equal to 0. So if a is equals to 0 and b is not equal to 0, then we have b cos Ka is equals to 0. This is just substituting in the solutions of the simultaneous equation. That is, when A is equals to 0, then B cos Ka will be equal to 0 from equation number 5, and from this we can say that if B is not equal to 0, cos Ka has to be equal to 0. That's why Ka will be equal to cos inverse of 0, which is nothing but n pi by 2, where n is odd term, that is 1, 3, 5, so on. And when you rearrange, you get K value which is equals to n pi by 2a. So this is for odd term. Then again second case is that A is not equal to 0 and B is equals to 0. In that case, if you substitute in equation number 5, we get A sin Ka is equals to 0. Here A is not equal to 0 but B is 0. That's why sin Ka will be equal to 0. So Ka will be equal to sin inverse of 0, which is equal to n pi by 2, where n is even numbers, that is 2, 4, 6 and so on. So K will be again equal to n pi by 2a. So we can just write it in general that K will be equal to n pi by 2a, where n is all natural number. Here we are not taking n is equals to 0, because if n is equals to 0, there is no meaning for the wave function, because the total wave function is going to vanish, which means the particle is having just 0 energy, which is not possible, because the particle will not be at rest within the square well. It is having certain kinetic energy. So by using this equation, we can find out the energy eigenvalue also. So let us square this equation, which will be k square equal to n square pi square by 4a square. When you just use the formula of k square, which is equals to 2me by h cross square. This is what we have taken while taking equation number 3. So that will be equal to n square pi square divided by 4a square. So here we are having the energy term, which is E. So when you rearrange it, we get the energy eigenvalue, which is equals to n square pi square h cross square divided by 8ma square, where n is all natural number, that is running from 1 up to n. And based on this, we can say that energy is not continuous, because we are having n is equals to 1, 2, 3, 4. We don't have the energy for n is equals to 1.5 or 1.3 or 3.5. So because of this, we say that for a particle in an infinite square well, the energy is discrete in nature. Then based on this formula, we can relate all the energy states, that is E1 is to E2 is to E3 will be equal to E1 is to 4 times E1 is to 9 times E1 is to so on, because E is directly proportional to n square, and we can just see for any particle of mass m, all other terms are going to be constant. That's why it is only depending on n value. So E is directly proportional to n square. So when you are getting any question where you need to find out the energy for, let us say, fifth state in an infinite square well, then you can directly say that it is equals to phi square, that is 25 times of E1, which is the energy of first state. So this is the use of understanding the energy eigenvalue. Then let us see about the energy separation in order to understand totally about the nature of a particle within the infinite square well. So by using the same equation we can find out the separation between the energy states. Here we need to consider the higher state energy minus the lower state energy, that is En plus 1 minus En, which will be equal to, the variable is only with respect to n. So in place of n square we are writing n plus 1 whole square minus n square. So when you solve it, the bracket comes up to equal to 2n plus 1 and the other term is nothing but 1 pi square h cross square by 8 ma square, which is the energy for n is equals to 1 state, that is denoted as E1. Let it be equation number 8. So by using this equation we can find out the energy separation, that is what is the energy difference between the second state and the first state. So that will be equal to 2 into 2 plus 1 times E1. So it will be equal to, 2 into 1 plus 1, because n is with respect to the lower state. So it will come up to 3E1 and next higher state E3 minus its lower state E2 will be equal to 2 into 2 plus 1, that is 5E1. Similarly the higher state will be 7E1 and furthermore. So energy separation is going to be in terms of 2n plus 1, whereas energy of the state will be with respect to n square. So based on the energy separation, we can say that the energy levels are not equidistant, because we have considered the consecutive energy differences. We are not considering the energy difference between higher states with the first state. So here the conclusion is that they are having different energy differences and they are not equidistant. So this is about energy eigenvalue and the separation between the states. Next let us see about the eigenfunction. So we have already seen that xi of x is equals to a sin kx plus b cos kx. So here a and b are acting as a normalization constant. So here we need to find out what is the value of a as well as b. So I am considering the first part as xi1 of x and second part as xi2 of x. Let us normalize one by one. First, normalizing a sin kx. We know that normalization condition is integration from minus infinity to plus infinity of xi star into xi into dx equal to 1. So xi star is nothing but a star sin kx, whereas xi is a sin kx. So when you multiply, you are having a star into a into sin square kx, but the limit is from minus a to plus a, because the particle is confined between minus a to plus a itself. It is not extending to infinity as in case of free particle. So this is the difference. In order to solve this integral, use the general formula, which is sin square kx is equals to 1 minus cos 2 kx divided by 2. So separately you can integrate, that is integration of 1 by 2 will be 1 by 2 into x for the limit minus a to plus a minus 1 by 2 as it is, integration of cos 2 kx will be sin 2 kx divided by 2k, that is the constant. Again limit is from minus a to plus a. Here k value is nothing but n pi by 2a. So when you substitute it, you get sin n pi. So the constant into sin n pi will be equal to 0, because in place of x you are substituting a and minus a. So finally you are getting the second term equal to 0. So we are having A value, which is the normalization constant for xi1 of x, is equals to 1 by root A. So finally, the normalized wave function xi1 of x will be equal to A sin kx, which is equals to 1 by root A sin kx. Similarly, consider the second part xi2 of x, which is equals to b cos kx, and when you solve it, again you find that the normalization constant is equals to 1 by root A itself. So xi2 of x will be equal to 1 by root A cos kx. So xi of x will be summation of these two, and we can just express it as xi of x for n is equals to even terms will be equal to 1 by root A, the sine function, that is sin kx sin n pi x by 2a, because k is equals to n pi by 2a we have already seen. And when n is equals to odd, which is 1, 3, 5 so on, then xi of x will be equal to 1 by root A cos n pi x by 2a. So this forms a complete set of eigen functions for a particle in an infinite square well. And already we have found out what is the energy eigenvalue, which is E is equals to n square pi square h cross square divided by 8 ma square. So based on this knowledge, we can plot a graph and find out what is the nature of the particle within the square well. So square well we have taken extending from minus a to plus a, and along y-axis we have the potential which is equals to infinity. Then let us consider the different states. Here I am considering first three states: n is equals to 1, n is equals to 2, n is equals to 3, corresponding to their energy E1, then 4 even, 9 even, because E is directly proportional to n square. So I am expressing each state with respect to the first energy state E1. Then we have the separation between the first two states, that is E2 minus E1 is equals to 3 times E1. Then E3 minus E2 is equals to 5 E1. Then further it will be E4 minus E3 is equals to 7 even, and so on. This is about the energy, its separation between the energy states. Then let us plot the graph for wave function, that is for n is equals to 1 and E1, what will be the nature of xi of x. So when n is equals to 1, which means that it is a odd term. So xi of x will be defined as 1 by root A cos pi by 2a into x. So we are having a cosine function, which is a symmetric function. Means when you consider this x is equals to 0 line, on the left side of x equal to 0, the nature of the wave function will be identical or symmetric with respect to the right side. And for the cos function, we know that when x is equals to 0, cos 0 will be equal to 1. That is the highest nature. And when x is equals to pi or pi by 2, when x is equals to pi by 2, that is at the boundary where potential is infinity, we have cos function equal to 0. That's why we can observe this type of nature for xi of x in case of n is equals to 1 state. So here for n is equals to 1, we are having just single curve. Then if you consider for n is equals to 2, which is a even term, then xi of x will be defined as 1 by root a sin n pi x by 2a. That is sine of pi x by a, because 2 will get cancelled out. And here we are having two different curves, and sine function, it is antisymmetric in nature, because if you take theta, then sine of minus theta will be equal to minus of sine theta, where you can explain the antisymmetric nature of sine function. So they are not going to overlap when you take the symmetry along x equal to 0. But if you consider cos function, which is the first curve for xi of x, there you are having cos function, that is cos of minus theta will be equal to cos theta. So cos function is symmetric in nature. That's why when you fold it along x equal to 0, the curve on both the sides of the square well will overlap, which explains the symmetry. But when you take it for n is equals to 2, which is a function of sine, then overlapping doesn't take place because sine is antisymmetric in nature. Another thing to remember is that here you are having the starting with respect to x equal to 0, and again it will just go on increasing and finally decrease. And in the same way you can define for n is equals to 3. For n is equals to 3, you are having three different sinusoids, where you will be having the cos function, that is when x is equals to 0 is there, the xi of x that will be having maximum extent, that is cos of the function which will be equal to 1. And again here also you can observe the symmetric nature. So this is about the particle which is confined within the infinite square well. The particle at the boundaries, you can see that xi of x is equal to 0, which means that there is no particle present at the barrier because of v of x is equals to infinity. So these are acting as impenetrable barriers. So this is about the eigenvalue and eigenfunction of a particle confined or trapped within the infinite square well or infinite potential well. So this is for today's class. In our next class, we will be studying about another application, which is about the simple harmonic oscillator. Thank you.